Hello, and welcome again to Advanced Physics for High School Students. This is Lesson 25, and its topics include Hooke's law and elastic potential energy. The lesson is in two parts. They're related to each other. Hooke's law is a law that deals with springs and elastic material that talks about forces. And then the related topic, elastic potential energy, has to do with the potential energy that's associated with what is tied up in a spring or a rubber band or some deformable object as a result of its being stretched or compressed. We'll take them one at a time, and we'll begin with Hooke's law. When we get into the classroom, hopefully you'll have an opportunity to get your hands on several different types of springs. And we want to look at some characteristics of springs. So I'm going to sketch a spring here, and we're going to talk about it a bit. Let's suppose that I have a wall and a floor, a corner here, that come together. And I'm going to attach a spring to this wall and just above the floor. So there's a crude diagram of a spring. And really this is kind of unrealistic because in fact, the spring would sag under its own weight. But let's suppose that I've got a spring that's stiff enough that's not going to sag under its own weight. In this position here, we say that the spring is relaxed. It is not stretched. It is not compressed. You could imagine that I could attach a block to the end of it, and that block would then sit on the floor, and the spring could push or pull the block depending on what kind of deformation the spring has. But right now, I just have a spring that is undeformed. It's in its natural state. We could measure the length of this spring if we wanted to, and we would say that whatever its length is when it's undeformed is going to be its natural length. And I will try to indicate that on this diagram. There are going to be some distances that we're going to be interested in looking at with this spring. And so I'm going to set up a coordinate system where I can mark a certain part of the spring and measure things with respect to that coordinate system. Since this is a horizontal spring, I could use X as my variable, but if it were hanging vertically, I could just as well use Y. I want to put an origin of my coordinate system at some point on the spring. I'm going to choose the right end of the spring, but I want to put a place where I can say this is where the spring is when there is no deformation to it. It is at its natural length, and I'm going to mark a point on the spring and call that my origin. And then I can talk about if I stretch the spring, how that the spring has a positive displacement, or if I compress the spring, that the spring has a negative displacement. So I could mark off points on this coordinate system. X equals 1 centimeter, 2 centimeters, 3 centimeters in the positive direction. X equals -1, -2, -3 centimeters in the negative direction. Or you can use inches, or you can use meters, or miles, or whatever distance happens to be convenient for you. We're probably going to be doing mostly with centimeters with real springs. So I can compress the spring, and the spring is going to resist that compression. I can stretch the spring. The spring is going to resist that stretching. It's going to try to return to its natural length. Eventually, we're going to attach masses to springs, and we're going to deform the spring and then let the system go, and the spring is going to oscillate. So that eventually we're going to describe the motion of a mass that's attached to the spring in terms of periodic motion. And that will take us to sines and cosines that's related to waves. So we will have a name for this origin. We're going to call that the equilibrium position, and we're going to borrow that language from waves in order to discuss springs. So if the spring resists this deformation, how much force does it exert? That was studied by Robert Hooke back in the era of the late 1600s, about the same time that Isaac Newton was working. And he studied these springs and developed a relationship that if the spring is not deformed too much, then there is a linear relationship between the amount of displacement that the spring experiences and the force that it exerts as a result of that. That's called Hooke's law, and it looks like this. Hooke's law says that the force that the spring exerts is equal to K times X, where Fs stands for the magnitude of the force that the spring exerts. X refers to the amount of deformation, and K is something that is called the spring constant, which is a number that's related to each individual spring. The spring constant is a number that will be unique to each spring. It's not a number that's the same number for every problem that you'll work, say in the case of the electrostatic constant when you dealt with Coulomb's law. Here we run up again with the fact that there are the same letters used to mean different things in physics, but we have that to deal with. This wasn't a decision that I myself made. It's been used by physicists for generations, and so it's just something that you're going to have to get used to. But each spring will have its own spring constant. The spring constant is a number that's related to the stiffness of the spring. If I have a very strong spring, say like the springs on the automobile of my car that keep the body off the wheels, I would have a number for the spring constant that's very big. Whereas if I have a very soft spring, a small spring, say like a watch spring, then the spring constant for that would be a number that's very small. And if I look at the dimensions, if force is measured in newtons and the amount of deformation is measured in meters, then the units of the spring constant are going to be newtons per meter. We don't have a special name for it. That's just the way that it's expressed, newtons per meter. This equation is very important, and it looks different than the way that your textbook writes it. And let me point out what some of the differences are. Your text puts a negative sign in front of the K, and it says that that negative sign represents the fact that the direction that the spring exerts its force is opposite the direction of its displacement. In other words, if I pull the spring, this spring in this diagram, to the right, then the spring is going to exert a force to the left. Or if I compress the spring, if I make X a negative number, then the spring is going to exert a force to the right. I prefer to write it without a sign and to draw a good diagram showing the direction that the force is exerted as a result of the spring, and then use that to help me solve problems. So that's an important difference in the way that I'm writing the formula F is equal to Kx, as opposed to your textbook F is equal to negative K delta X. And your authors use delta X to represent the displacement of the spring. I'm using it for the amount of deformation.